Okay? So at the end, we remove everything. I mean, both subsequences are empty, and result is in order. Why is it in order? Because the two sequences initially they were in order. Okay? The two sequences initially they were in order. So when we compare the first element, we are comparing the smallest element of A1 with the smallest element of A2. Now, the smallest of the smallest and the smallest is going to be the smallest of result of both of them. Okay, so 1 is the smallest element of A1. 2 is the smallest element of A2. So what is the smallest of these two is 1, which is the smallest element in both A1 and A2. Right? You have a family, and X is the smallest, is the youngest member of family 1, and Y is the youngest member of family 2. If X is younger than Y, then X is the youngest member of both families. That's what I'm saying here. So the result at the end, we are going to put the smallest element followed by the next smallest in both sequences, followed by the next smallest in both sequences, followed until we get the sequence in the right order. Okay, so again, so that we don't lose the picture, we are dividing into smaller subsequences, and then we are merging into bigger in order to compute the sorted sequence again. So what happens, for example, in this stage is that we are comparing 4 and 8. So we put 4 in result, and then we compare what? 9 and 8, so we put 8, and finally 9 is the remaining one, so we get 4, 8, 9, 4, 8, 9 like this. And we are doing this the same here, and we are doing it like we saw in the example here. So dividing, and then conquering, partitioning, and then merging. Now, but by looking at this example here, okay, let's get the bigger picture, maybe it's better. How many steps do I need to do this partitioning? The last one, the last merging. How many steps do I need? So I have an array A1 has 5 elements, array A2 has 5 elements, and I want to merge them into a result which has 10 elements. How many steps did I need to do the merging? Yeah, it was 10 steps in this example. It might be less, but the worst case is 10. Okay? So this was, let's say, 5. This was 5 steps plus 5 steps. No. Come on. That was 5 steps plus 5 steps. This one was in the worst case is 3 steps, 3 comparisons plus 2 comparisons. This one in the worst case 3 comparisons plus 2. I'm not sure about the best way to explain that. Okay, let me draw you something. Okay. So that's our original sequence. It has size n. we divide it into roughly n over 2 and n over 2 size sequences, and we keep dividing until we reach sequences of size 1. Okay? Now, that's the partitioning. Now the merging, we are starting from sequences of size 1, and we are merging them into sequences of size 2. Sequences of size 2. Let's say the original sequence has size 8. So what we get is that we have 8 sequences of size 1. And we merge them into sequences of size 2 each. Okay? And then we merge these into sequences of size 4. And then we merge this into a sequence of size 8. Now, this merging here, we said it costs, in the worst case, 8 steps. This one's cost, in the worst case, 4 steps. This one causes, in the worst case, 4 steps. This one causes, in the worst case, 2, and this one 2, and this one 2, and this one 2. Now, what do we see is that at each merging level, here we have 8 steps, and here the total is 8, and here the total is 8, etc. And yeah, so each level is 8, and 8 is the size of the original sequence. So if the original sequence has size 32, for example, then in the worst case we will see 32 in every stage. It will be 32 and then 16, 16, and then 8, 8, 8, 8, and then each 8 has a 4, 4, etc. So that's what I wanted to say, is that at every merging level, what we are doing a total amount of work which is equal to the size of the input n. So at each level, we are doing n, big O of n of complexity, of work. Okay, at each level, it's big O of n. So it's big O of n here, big O of n here, big O of n here, etc. Now, this is like our first step to understand the complexity of merge sort. Now, in order to find the complexity of merge sort, we need to know how many of big O of n do we have. Okay, so this is input of size n. There is a lot of partitioning going on, and we get n of these, and then we merge these, and this merging costs also big O of n, and then we merge and it costs big O of n, blah blah blah, and it costs another merging and it costs big O of n, and then we merge and it costs big O of n, blah blah blah, and it costs another merging and it costs big O of n. Now, how many of these do we have? Because the complexity is going to be big O of n times, it is repeated a number m times. It's big O of n times m. But what is this m really? That's what we need to know. We need to know what is m in terms of the input, in terms of the input size. So let's think of a concrete example. Let's say our sequence has originally size 16. So we are going to divide until we reach 16 single sequences, or size 1 sequences. Now, how many merging do we need to do now? So we do the first level of merging to get sequences of size 2, and then we do these are sequences of size 2, and there is another merging to get sequences of size 4, and there is another merging to get sequences of size 8, and there is another merging to get a sequence of size 16. So how many merging do we need? 4. Now, what is 4 in terms of 16? 16 is 2 to the to the power of 4. I'll give you a hint. It's a logarithm. So n, that's n. It's equal to 16, which is 2 to the power of 4. So what is 4, which is the number of merging? That's log 2 of n. I mean, we said if we have log 2 of 2 to the 4, what's that equal to? Yeah, 4. Log 2 of 2 to the 4, that's going to be equal to 4, because we said that this 2, they cancel out, and we get 4. Okay, so the input size is n, and the number of merging is going to be, log of n. So we said that the complexity was what? The complexity, we had big O of n in every merging level. And then we said the number of merging levels is m. So m equals what now? M equals, in terms of n, yeah, log n. So the complexity of merge sort is going to be big O of n times, yep, big O of n times big O of log n, and that is equal to big O of n log n, and that's our log linear algorithm. So the complexity of merge sort is n log n, and we have seen how n log n is a lot better than n squared. So selection sort, insertion sort, they both were n squared in the worst case. This one is going to be n log n in the worst case. So we have talked about the description, an example of the algorithm, how it works, and from how it works, we were able to derive the complexity of the algorithm. Now all we have to do is to look at how the algorithm works. So it's easy. It's a recursive. It's going to be a recursive algorithm. Divide and conquer are recursive algorithms because we start from a problem and we recursively divide it into smaller problems, and then recursively build the solution from the smaller solution. So recursive dividing, recursive conquering. In terms of merge sort, there is a recursive partitioning and then a recursive merging. Okay, so this is the base case of the recursive call. If the size of the array is is 1, then we stop the partitioning. Otherwise, we are going to create an array, half an array, and then the second half of the array, not exactly the same size. They will differ by either 0 or 1, depending if the original sequence is or not the original sequence. The mother sequence is for at any recursive call has size either even or odd. So we create two sub arrays, and we recursively we are going to do the merge sort for them. Okay. Because this is what we saw. Every stage we are doing the same thing. At every stage we divide, and then at every stage we merge, and that's why it's recursive. We are repeating the same thing, and then we are merging the result of the arrays in these recursive calls, like the merging we have seen here. So this is a merging. This is a merging. This is what this merging is. This merge routine is saying. So there is merge sort, which is the algorithm, and there is merge function, which is going to put two sorted sequences into one single sorted sequence. Now, how does it do that? Is by this function here. This is what we have seen. So we have two subsequences, and we are going to compare the first element of the first subsequence with the first element of the second subsequence, and we take the smallest and we put it in result. So this is the merge routine. So we have merge sort. So this is merge sort. Okay, it's merge sort. It calls merge function. This is merge sort with comments for you to understand. This is an example of the merge routine. We have seen an example of the merge sort. And this is the merge routine itself, the one that merge sort calls. And this is the same one, merge routine, but with comments for you to understand. So let me just check if there is anything in merge that I need to. Merge sort works in two stages: partitioning and merging. During merging, this is what happens. This is cool. I can click on the figure and it takes me there. I can click on the figure and it takes me there. Okay, so we have already explained that. We have already seen examples. We have already talked about the asymptotic complexity. So we have talked about the asymptotic complexity of the merging operation, which is n log n. We have not talked about the complexity of the partitioning operation. Now, the complexity of the partitioning operation is not a big deal. It's going to be big O of n. You can read it from the slide. If you don't understand it from the slide, email me. The partitioning part is big O of n. So partitioning is big O of n. And then we have merging, which is big O of n log n. And obviously, if you put this together with this is gonna win the n log n one, and this is why merge sort is n log n. This is the thing that I have explained when I draw the dividing and the dividing of the sequence and the merging of the sequence. When I said that each stage has got big O of n work, and this is what I said in the previous slide. I'm just looking for the next thing. The problem. That's the problem with merge sort, is that we need extra space. Because if you look at the algorithm again, where is the algorithm again? There it is. So that's merge sort. We are going to partition. We can partition inside the same array. Okay, so that because partitioning is just passing indexes around. We don't need to create a new array to do the partitioning. We don't need that. But when we merge, we are going to need a new array. We cannot put the same elements inside the same array. In order to merge, we have to create a new array. Not put the same elements inside the same array. In order to merge, we have to create a new array. So merge sort is going to take an array A and is going to produce another array B. Insertion and selection sort, they don't do that. They work inside the same array. So inside the same array, we are going to do swapping or shifting. We don't get out of this array. So we don't use extra space. Well, we use extra space for temporary variables, but it's not for the whole sequence. So extra space in other algorithms is called is constant. Few extra space for the temporary variable, for holding the index, the current minimum index in selection sort, or holding the value that we are going to compare to in insertion sort. This is extra space which is constant. However, in merge sort, the extra space is linear. So this is a sequence, and we need a new sequence here. We need a new space. We need a new array, so that when we do the merging, we copy it over here, and we merge and we merge and we merge, recursively merge, until we build the new sorted sequence. So that's the problem with merge sort. That's the biggest problem with merge sort. It requires big of an extra space. So if you have an array of a million numbers, then you need an extra array of a million numbers to hold the results. So as you can see, we have improved the efficiency of merge sort, but at the cost of adding extra space. Now in the next lecture, we're going to see quicksort, and we will see more about merge sort. We will see the other problems with it. So we are going next lecture to give a quick summary of merge sort and start doing quicksort. So now our motivation is we have reached an algorithm which is log linear. It's n log n. However, it uses extra space. Now, can we find an algorithm which is n log n but does not use extra space? And this is what we're going to see in the next lecture when we do quicksort. We're going to see different variations of quicksort. Now, do you have any questions? Okay, then see you in 2 weeks' time. Yes. Yeah, what about it? One, two, three. Shall I just send you the solutions? Yes. I don't know. I mean, any kind of questions. I think students of your caliber can answer any kind of questions.